Today we shall going to start module 1 of chapter 4. In this module we are interested to discuss Routh's process for the ignoration of coordinates. So far we have discussed the Lagrange's equations of motion which describe the motion of a dynamical system under different types of constants. In Lagrangian mechanics, generalized coordinate qk, generalized velocity qk dot are treated as Lagrangian variables where time t is treated as parameter. There are another type of formulation which is known as Hamiltonian mechanics. This formulation is developed with the help of a new function known as Hamiltonian. This dynamics is applicable for Hamiltonian system only. We shall discuss this in this module. In this module, we shall discuss about the necessity of Hamiltonian dynamics. We shall define cyclic coordinates and its uses. Conservation theorem for generalized momentum will be discussed in this module. Next, Routh's process for the ignoration of coordinates will be discussed in detail. Let us define cyclic coordinates. A coordinate qk is said to be cyclic or ignorable if it is explicitly absent in the Lagrangian function L. Thus, if qk is a cyclic coordinate, then L is a function of only generalized velocity qk dot and time t. That is, in this case, we have L equal to L function of qk dot and t. Thus, we have del L del qk dot equal to 0. We can use this definition in conservation theorem for generalized momentum. Lagrange's equation of motion corresponding to the coordinate qk is given by ddt of del L del qk dot minus del L del qk equal to 0, where L is the Lagrangian. If qk is cyclic coordinate, then del L del qk equal to 0. This gives from the Lagrange's equation of motion ddt of del L del qk dot equal to 0. Thus, we get del L del qk dot equal to constant. If we write del L del qk dot is equal to pk, where pk is the generalized momentum, then we have pk equal to constant, where pk is the generalized momentum corresponding to the generalized coordinate qk. Thus, we have the generalized momentum conjugate to a cyclic coordinate is an integral of motion. Let us consider an example. The Lagrangian of a particle of mass m moving in a central force field is given by, in polar coordinates, L equal to half m into r dot square plus r square theta dot square minus v function of r. First term gives the kinetic energy, whereas the last term gives the potential energy. We know that Lagrangian is the difference of kinetic energy and potential energy. Discuss its motion. Clearly, r and theta are the generalized coordinates, and here theta is absent in the Lagrangian L. So, theta is the cyclic coordinate here. Thus, the generalized momentum corresponding to the cyclic coordinate theta is p theta. Therefore, p theta equals to del L del theta dot. This gives p theta equal to m r square theta dot. From the property of cyclic coordinate, we have m r square theta dot equal to constant. This shows that angular momentum of a particle is a constant of motion. Lagrange's equation of motion corresponding to the r coordinate gives ddt of del L del r dot minus del L del r equals to 0. Therefore, m r double dot minus m r theta dot square plus del capital V del r equal to 0. This can be written as m r double dot minus p theta square divided by m r cube plus del capital V del r equal to 0. Here we have used the relation between theta dot and p theta already obtained. As p theta is constant, so we have to deal with only one degree of freedom, which is r. Now we shall discuss Routh's process for the ignoration of coordinates. For this, we consider a dynamical system with n degrees of freedom, that is, a dynamical system containing n number of particles and specified by n generalized coordinates q1, q2 up to qn. Let the system has j cyclic coordinates which are q1, q2 up to qj. Please note that j must be less than n. We shall show that the dynamical system has n minus j degrees of freedom. Clearly, the generalized momenta pk equal to del L del qk dot equal to constant. Here L is the Lagrangian of the dynamical system, pk is the generalized momenta corresponding to the generalized coordinate qk. If we take the constant as beta k, then we have pk equal to beta k for k equal to 1, 2 up to j. Let us define a new function capital R by capital R equal to capital L minus summation k equal to 1 to j beta k into qk dot, where capital L is the Lagrangian of the system, qk dot are the generalized velocities and beta k are the constant values of the generalized momenta. If a coordinate corresponding to translation is cyclic, then the system remains unchanged due to translation. One can say that if a system remains invariant under translation along a definite direction, then the corresponding linear momentum is conserved. This property is closely associated with the symmetry of that dynamical system. Now, the function r can be written as r is a function of generalized coordinates q suffix j plus 1, q j plus 2 up to qn, functions of generalized velocities q j plus 1 dot, q j plus 2 dot up to qn dot, and beta 1, beta 2 up to beta j and time t. R is the Routhian function. Let us calculate the virtual change of R, which is delta R. Delta R can be written as delta L minus summation over k delta beta k into q k dot minus summation over k beta k into delta q k dot. We get this result from R equal to L minus summation over k beta k into q k dot. Taking the differential, we get equation 4.4. Now, the Lagrangian L is a function of generalized coordinates q j plus 1, q j plus 2 and so on qn, generalized velocities q1 dot, q2 dot up to qn dot and time t. So, delta L can be written as summation over k, k varying from j plus 1 up to n, del del qk of L into delta qk plus summation over k, k varying from 1 to n, del del qk dot operated on L into delta qk dot. Please note that we have used the chain rule of differentiation. As L depends on generalized coordinates q j plus 1, q j plus 2 up to qn, so here the summation stands for k equal to j plus 1 to n, whereas in the second term k runs over 1 to n, since L depends on q1 dot, q2 dot up to qn dot. Here qk dot means ddt of qk. Delta is the virtual change. Now, the second term can be written as summation over k equal to 1 to j and then summation over k equal to j plus 1 to n. So, from two terms we get three terms which have been written in equation 4.5. Substituting the expressions for delta R and delta L, we get the equation which have been written in the first two lines. Since del L del qk dot equal to beta k for k equal to 1, 2 up to j, using this result we get the equation 4.6. Two terms cancel each other and we get equation 4.6. Equation 4.6 involves changes delta qk and delta qk dot. Here k varies from j plus 1, j plus 2 up to n and delta beta k where k varies from 1, 2 up to j. These are arbitrary and independent variations. This leads to the following equations. Del R del Qk equal to del capital L del Qk, del capital R del Qk dot equal to del capital L del Qk dot. These equations are valid for k equal to j plus 1, j plus 2 up to n and minus del capital R del beta k equal to qk dot for k equal to 1, 2 up to j. By Lagrange's equation of motion, we have ddt of del L del qk dot minus del L del qk equal to 0 for k equal to j plus 1, j plus 2 up to n. Please note that there are first k cyclic coordinates which are q1, q2 up to qj. Using 4.7, we have ddt of del R del qk dot minus del R del qk equal to 0 for k equal to j plus 1, j plus 2 up to n. From 4.8, we have qk equal to minus integration del R del beta k into dt plus integrating constant. This relation holds for k equal to 1, 2 up to j. Thus, capital R behaves as the Lagrangian capital L of a new dynamical system which have n minus j degrees of freedom. That is, the degrees of freedom has been reduced here. Consider an example. In a dynamical system, the kinetic energy and the potential energy are given by capital T equal to half q1 dot square divided by a plus b q2 square plus half q2 dot square. Capital V equals to c plus d into q2 square. A, B, C, D all are constants. There are two generalized coordinates which are q1 and q2. We have to determine q1 function of t and q2 function of t by using Routh's process for the ignorable coordinates. Here, Lagrangian is given by capital L equal to half q1 dot square divided by a plus b q2 square plus half q2 dot square minus c minus d q2 square. Since Lagrangian is the difference between the kinetic energy and the potential energy for a holonomic dynamical system. As in the expression of the Lagrangian, q1 is absent but q1 dot is present, so q1 is a cyclic coordinate. Thus, del L del q1 equal to 0. Generalized momentum corresponding to the coordinate q1 is p1 equal to del L del q1 dot, which is constant as q1 is a cyclic coordinate. If we take the value of the constant as beta 1, then we have q1 dot divided by a plus b q2 square equal to beta 1. Now, the Routhian function is given by capital R equal to capital L minus beta 1 q1 dot. If we put the value of Lagrangian L, then R becomes capital R equal to half q1 dot square divided by a plus b q2 square plus half q2 dot square minus c minus d q2 square minus beta 1 q1 dot. On simplification, this gives capital R equal to half beta 1 square into a plus b q2 square its whole square divided by a plus b q2 square plus half q2 dot square minus c minus d q2 square minus beta 1 square into a plus b q2 square. Finally, R becomes capital R equals to minus half beta 1 square into a plus b q2 square plus half q2 dot square minus c minus d q2 square. The equation of motion for the coordinate q2 is ddt of del r del q2 dot minus del r del q2 equal to 0. That is q2 double dot plus beta 1 square into b into q2 plus 2 into d into q2 equal to 0, which gives q2 double dot plus capital S square into q2 equal to 0, where capital S square equal to beta 1 square into b plus 2d, which is nothing but a constant. On integration, we have q2 equal to capital B sin capital A into t plus epsilon, where capital B and epsilon are arbitrary constants. Again, we have q1 dot divided by a plus b q2 square equal to beta 1. If we put the value of q2 here, then we get q1 dot equal to beta 1 into a plus b q2 square equals to beta 1 into a plus b into capital B square sin square capital A into t plus epsilon. On integration, this gives q1 equal to beta 1 a into t plus half beta 1 small b into capital B square integration 1 minus cos 2 into capital A into t plus epsilon dt. On integration, q1 becomes q1 equal to beta 1 a into t plus half beta 1 b into capital B square into t minus 1 divided by 4 into capital A into beta 1 b into capital B square sin 2 into capital A into t plus epsilon plus integrating constant c. In this module, we have discussed a reformulation of classical mechanics which is known as Hamiltonian mechanics. It is described with the help of a new function which is known as Hamiltonian. So far, in Lagrangian mechanics, the generalized coordinate qk, generalized velocity qk dot was treated as the Lagrangian variables, whereas time t as parameter. But in Hamiltonian mechanics, the generalized coordinate qk and the generalized momenta pk are treated as Hamiltonian variables. In this module, we have discussed the Routh's process for the ignoration of coordinates, Noether's theorem, cyclic coordinates and its uses.